The next topic that I want to talk about is that of the center of mass, which for us is also going to be known as the center of gravity, which will also be known as the centroid. To begin with, we're going to look at a relatively simple situation. I'm going to imagine that I have a long, thin piece of balsa wood or some other extremely lightweight material whose weight I can ignore for the purposes of this calculation, and I'm going to glue objects to the piece of balsa wood. These objects may have different weights, they may have different masses. Each one of them has a position somewhere along this piece of balsa wood, and the question that I want to try to figure out is, if I were going to make a seesaw out of this, at which point would I have equilibrium? At which point would it balance? Just as much tendency to turn clockwise as turn counterclockwise. I'm going to call the location of such a thing x bar. I'll call that the center of mass, center of gravity, also known as the centroid. Each of my objects has an x-coordinate to go with it. I can index them in any order that I want, so I'll just pick an arbitrary order. So I'll call the x-coordinates of various objects x1, x2, x3, and x4. In physics, the tendency of an object like this to make the piece of balsa wood turn is measured by the weight or mass of the object multiplied by how far out from the fulcrum, the balance point, you are. In physics, the torque is the force, the weight, or equivalently for us, the mass, times the lever arm. If I look at the first of my objects, it's located at x equals x1, which is larger than x bar by an amount, x1 minus x bar. That number will be positive. If I multiply that by the positive number m1, we're going to call that the moment about the x bar location of object number 1. In this case, it'll be a positive number because x1 is bigger than x bar. Because x1 is to the right of x bar, the contribution to the torque is going to try to make the beam turn in a clockwise direction. In the diagram, object number 2 is to the left of x bar. If I calculate x2 minus x bar, that number will be negative. Multiply by the mass number 2, the result will be negative. This is going to be a tendency to make the beam of balsa wood turn in the counterclockwise direction, and we'll indicate that by recognizing that this contribution is negative, not positive. In general, if I look at an index 1 to n, where n is the number of objects that I have, the moment of object number I will be mass or weight number I times xi minus x bar. This number will either be positive or negative. It will either contribute to turning in the counterclockwise direction or in the clockwise direction, depending on the sign. To get the overall behavior of the system, we will add up all of these different contributions and see if it's positive, which will correspond to turning in one direction, negative, which is going to correspond to turning in the other, or if it's zero, that's going to mean we're at the balance point. There is no tendency to turn either to the left or to the right. So if I want to identify the balance point, x bar, I'm going to have to find a number x bar so that this equation is true. For clarity, I'm going to write out what you get if you have exactly 4 terms, although the same sort of argument will work for 4 terms or 10 or 50 or a million. Being literal minded about it, if n is 4, my equation turns into this. I'm going to simplify this some more. This looks worse instead of better, but if you'll notice, some of the terms have x bar in them and the others don't. So I'm going to move all the terms that contain x bar over to the other side of the equation in an effort to try to figure out what the x bar actually is. Once I've done that, I see that over on the right-hand side, which is the only place x bar appears now, every term has exactly one factor of x bar, so I can factor the x bar out and rearrange things. After doing that, I can divide through by the number m1 plus m2 plus m3 plus m4, and I will have isolated the x bar, and I'll know the center of mass. So to calculate the center of mass, I form two different sums. On the bottom of the fraction, I just add up all the masses of the objects. In the numerator, it's more complicated. I take each mass, multiply it by the corresponding coordinate of the object in question, add all of those up, and then once I've done that, the fraction is equal to the location of the center of mass. Obviously, if I had 5 objects, I would have an m5x5 upstairs, and then plus m5 on the bottom, and so on and so forth. So this painlessly generalizes to any number of objects. So x bar is going to be the sum I equal 1 to n of mass number I times x number I, divided by the sum of all of the masses, which we'll also call sometimes the total mass of the system. As an example of this sort of thing, let's imagine that we have 3 points. x1 equals 4 is the location of the first object, m1 equals 10 is its mass, x2 equals 9 is the location of the second, m2, the mass of the second object, is 6, x3 is negative 1, m3 is 4, and I'd like to calculate the location at which this would balance. Putting the numbers into the formula that we figured out, the center of mass, also known as centroid, also known as center of gravity, is located at x equals 4.5. As a slight generalization of this, I could imagine that I had a set of points in the xy plane. Each one of them represents an object with a certain mass. Each one of them has a location in the plane, which will be given by the x-coordinate and the y-coordinate. As before, I'm going to let n represent the number of objects that I've got. In a similar way to before, I'm going to imagine that these objects have been glued to a big piece of some extremely lightweight material whose mass I can ignore. And then I'd like to take this plate that I'm looking at and try to find a place where it's going to balance. That is to say, there's no tendency to turn to the left or to the right or in the up and down direction. If you make an argument that's similar to what we did before, the following result follows. The center of mass has x-coordinate x bar, y-coordinate y bar. X bar is calculated using exactly the same formula as we had for the one-dimensional system, and since in this context x and y are completely independent of each other, it's reasonable to think that y bar is given by the same formula that x bar was, with every reference to x replaced with a reference to a y-coordinate instead. We need to do a little example of this, and then we'll talk about a rather odd notation. I'll have 3 objects located in the xy plane. x1, y1 is going to be the point 1, 2, meaning of course that x1 is 1 and y1 is 2, the mass of object number 1 is 10 units of mass. x2, y2 is at the point 4, 0. x2 is 4, y2 is 0. The mass of object number 2 is 20 units of mass. x3, y3 is located at 5, 6. x3 is 5, y3 is 6. The mass of the third object is 5 units of mass. I'd like to calculate the center of mass of this two-dimensional discrete system. Putting the numbers into the formula for x bar, I find out that x bar is 3.2857 to 5 significant figures. This is just a little bit more than 3 1/4. The x-coordinate of the center of mass is just a little bit bigger than 3.25, 3 1/4. In the picture, I'll draw that in. The center of mass is somewhere on that vertical line. If I figure out what the y-coordinate of the center of mass is, I'll know exactly where it is. The y-coordinate works out to be just a little bit bigger than 1.4. I'll draw that in on my picture as well. Having found both the x-coordinate and the y-coordinate of the center of mass that completely locates that point, I've drawn it in, written center of mass, and drawn an arrow at it. In this video, we've seen how to do centers of mass problems for one-dimensional collections of a finite number of objects, and also how to do that in the case of 2 dimensions. What we're going to talk about next is how do we find the center of mass for an entire region of a plane that's made up of an infinite number of points. I hope everyone's having a good day. I'll talk to you again soon.